Now it's 11. So we will have today's last talk. Yunze will tell us something about the infinity category. So in particularly, the topic is adjoint functors, presentability, and tensor products.
All right, so first, of course, I want to thank Wuchuan for the introduction. And also I want to thank the organizers for organizing this event. It's my pleasure to have a chance to speak here. And also thank all the audience for coming. All right, so I will, for this talk, I will be talking about some aspects of infinity categories. In particular, I will be talking about adjoint functors and presentable infinity categories. So in the schedule, you can see that there is also a topic called tensor product. And in fact, next Monday, I'm also going to give the next talk on infinity categories, where I will be talking about smash products, stabilizations. So I would like to postpone this topic and combine it with my next talk. So before I start, let me claim that most of the things I will be talking about are coming from the following two resources. So first, we have the higher topos theory by Jacob Lurie. And since I guess the previous speakers are following Marcus Land's book, so I will also be using and following the lecture notes as well. So that's Marcus Land, and the book's name is Introduction to Infinity Categories. In particular, the fifth chapter of this book is mainly on adjunctions and adjoint functor theorem. So I will follow this for the first part of my talk, and for the presentable infinity category part, I will be more leisure and going loosely and presenting some results extracted from Louis Heyer's topos theory. All right, so I will start with talking about adjunctions. So first, let me define what is, maybe I should first quickly review what is an adjunction or what are adjoint functors in classical category theory. So if you have one category C and D and two functors between them F and G, then we say F is left adjoint to G and G is right adjoint to F. Or this is an adjunction if there is a natural bijection between home sets. The left-hand side is the home set from fx to y, and the right-hand side is the home set from x to gy for any objects x in C and y in D. So, of course, in the infinity categorical setting, we would like to expect something similar. And since now we don't have we don't have mapping home sets anymore, and we're caring about mapping spaces. So we expect to enhance all this stuff to the level of spaces. So let me first give the definition of an adjunction. So we will be using some techniques developed from yesterday, namely the notion of Cartesian and co-Cartesian fibrations. So an adjunction is a functor between infinity categories, which is from infinity category E to the infinity category delta 1 that is simultaneously a Cartesian and co-Cartesian fibration. So I will call it a bi-Cartesian fibration. So using the straightening and unstraightening technique we also discussed from yesterday, So we can extract from this data, this bipartition vibration, two functors. So using the straightening, unstraightening techniques. So for example, we take 0 in delta 1, we can have the fiber of this over 0. So we have an infinity category E0, which is the fiber over 0. And we also have a category, infinity category E1, which is the fiber over 1. So because this P is a co-Cartesian vibration, so we can get a functor from E0 to E1, which if you want to have a reference, you can go back to yesterday's lecture notes. So we can use this Cartesian vibration, co-Cartesian vibration, to get a functor f from E0 to E1. And similarly, using spherically, you can get a functor g from E1 to E0 using the fact that the P is a Cartesian vibration. So, and in fact, I will revisit some aspect of this construction later. So that is, given such an adjunction functor P, we can get two functors and two infinity categories, E0 and E1. And we say that F is left adjoint to G, and G is right adjoint to F. And we will basically write like this. So in the more general setting, here is a quick remark that if you have a functor, say F between two infinity categories, so F is a functor from C to D, we say that F has a right adjoint. If there exists such an adjunction, P from being a functor from E to delta 1, and such that we have some equivalences like C is equivalent to E0, and this is F from P, the left adjoint coming from this adjunction, and we have an equivalence of infinite categories from E1 to D as well. So this is what you can say if you just start with a functor between two categories and you want it to be a joint functor. So that's the definition of adjunction. So of course, we expect that, for example, we have I will stick to the E0 and E1 notation. So we have such an adjunction, and we would like to have something like a homotopy equivalence between these mapping spaces. So if we have X is an object in E0 and Y is an object in E1, we are hoping that we have such things like map in E1, Fx, Y is equivalent to the mapping space in E0, E0, X, Gy. So I will prove this result, or at least give a sketch of the proof of this result. So there, the proposition says that there is a natural equivalence of functors that is map E0. This is equivalent to this. So this proof will actually exploit the construction of these two functors from the adjunction data. Of course, our setting is that we have a P and then the adjunction here. So we'll exploit the construction, how we extract the data F and G from this adjunction, and let's give a sketch of the proof. So first, in this proof, we will use something which we will basically treat that as a black box. The main idea is to say that these two functors are both equivalent to this. So first, these two functors are both functors from this product of infinite category to the infinite category of spaces. And we want to say these two functors are both equivalent to the composite of this functor. That is, you include, because they are fiber in E, so include these two infinite categories into this E, and this is the mapping space functor to the category of spaces. So that's our goal. That is, we want to prove that we have such an equivalence between functors. So what we are going to do is that we will construct two natural transformations. And I will call them tau f and tau g. So tau g is a natural transformation from I naught composed with g goes to I1, and tau f is constructed, is going to be a natural transformation from I naught to I1 composed with f. And here I naught is the inclusion of E naught into E, and I1 is the inclusion of E1 into E. So the construction of these natural transformations relies on the lifting properties of these fibrations. So these two natural transformations are coming from the solving the lifting problem in the following two diagrams. So let me first draw the diagrams. So because the constructions are similar, so I will just talk about one of them. So because we know that this is a bicartesian fibration, so this gives us that in fact we can actually form the functor categories. So we will have the lifting, these two are also going to have the lifting properties. That is, they are also bicartesian fibrations. So, and we use the exponential adjunction, so we can shift things to have the canonical diagrams we want for lifting things. That is, what we can do here is that, for example, if we want to construct the lift here, we can use the exponential adjunction to rewrite these two to here. And on the left-hand side, what is left is this one point includes into the delta one, and we use the fact that this is the Cartesian fibration to construct such a lift. And it is not hard to just chase the diagram to verify that indeed you have these two natural transformations. So after you have constructed these natural transformations, then we can start to prove the statement that we have these two functors, this functor and this functor, are both equivalent to this composite functor. So I'll still just prove one side as an example. So that is, we make such a composed functors. That is, we look at so here, what we are doing is that the first step is we do this, use this tau g. So tau g is a natural transformation from I naught composed g to I1, which is this data is given as a functor from E1 times delta 1 to E. So we use tau g to map this to this, and we compose all these functors together. And we can check that this is a pointwise equivalence. And there is a theorem which we probably didn't go over, but there says that if you have natural equivalence, which is a pointwise equivalence, it is actually an equivalence. So this theorem, I believe, is, you can find it in the Marcus book 2.2.2, that pointwise equivalence is actually an equivalence. And so we get that this at the when you restrict yourself to the two sides between these two natural transformations, because you can still think about this data as a natural transformation between two functors. One of them is from is you use the use tau g's from I0 to I1 composed with f. So one of them is just you use I0 to put everything into E, and the other one is you compose with f and treat things as in I1. So this gives you an equivalence between this functor and this functor. And similarly, you can do the same thing to using tau f and using the same argument. So you can in fact prove that given this data, you have f and g are actually giving you the equivalence between functors. That is, you do have the desired property you want for adjoint functors that you have this result. So that's how we see we can use this similarly abstract definition of an adjunction to get to adjoint functors, and they do have the equivalence in the mapping spaces. And next, I'm going to define units and co-units for adjunctions. So recall that in the ordinary category theory, say you have a bijection let me be more specific. So you can say, for example, we take y equals f of x. So the identity map on the left-hand side will give you a morphism on the right-hand side by adjunction, so which reads as x goes to gfx. And by the naturality of adjunction, this gives you a natural transformation from the identity functor of C to the functor G composed F. So now we want to mimic this construction, and similarly, you also will have this is called unit. And so also you can do the same thing by setting x equals gy, so you will get fg natural transformation to id of d, and this is called co-unit. So, and they were going to satisfy the so-called triangle identities. And we wanted to also transplant all these things to the infinity-categorical setting. So we would like to, I'm going to briefly go over how do we define units and co-units. So we will still be using the two natural transformations we got. So they are tau g I0 composed g to I1, and tau f I1 goes to f composed, sorry. Goes to I1 composed with f. So we are going to form the following diagram. So let me first finish writing them. So we can form such a diagram and check that this diagram commutes. For example, if you restrict to, sorry, I'm going to say they are commute when you restrict to E1 times 0. So because when you have E1 times 0, the tau g is precisely this. And here you all tau f it starts with I0, so this is I0 composed with G, and this is I0 composed G. So this commutes. So because this diagram commutes at E1 times 0, so you can combine the two natural transformations to get the two the two which I mean tau g and tau f composed with g times id. So you can put them together to form a map from E1 times the inner horn to 0 to E. That is, you think about this inner horn as 0, 1, 2, and you define this as tau g here and tau f composed with g times id here. So you get a functor from here to here, and then you include this into delta 2. So you form such a diagram, and you can and the bottom map actually it maps here. It is the composition of the map from to delta 2. You project, and here you map 0 to 0 and 1 and 2 to 1. Anyways, so the idea is that you want to assemble these two natural transformations together to and use the extension property, lifting property, to fill the inner horn, so that you end up getting the desired the unit or the co-unit map. And in this case, so we can fill this this horn, and we will have so we have this dashed arrow as in the diagonal. So given this, so now we can look at things pointwise. So for example, if you take Z as an object of E1, so this part of data, if you keep track of the value of this on the 3 vertices, so it is giving you a diagram. So you notice at point 0, you have at point 0 you have I not composed with G, and at point 1 you have the image of tau G, which is just the inclusion, so you get Z, and at 2 you at this vertex, what you have is that you plug Z into this, so you get GZ composed with f of z, so you get f of gz. So if you look at things pointwise, in this you will get a diagram which is gz goes to z goes to f of gz, and by filling up this inner horn, you will get such a morphism. So, and if you put things pointwise and put them together, you will end up having this, which we want it to be the unit of the adjunction. And since that in our construction, I'm not going to verify that this diagram is well-defined and continuous, but the thing I want to point out is that because you have sent these 2 points, 1 and 2 to 1 in this bottom horizontal map, so that you are able to guarantee that this lies in the fiber of E over 1. So you end up really getting an element. This element is going to be an element in E1. So you do, and I will call this the unit of the adjunction. And if you do things dually, you will get the co-unit. So let me get to a new page. So the unit is going to be a natural transformation like this, and the co-unit is going to be a natural transformation, which has this is going to be similar to these two in the classical set. Okay, so that's about units and co-units. And now I'm going to go over some of the things that are just going to be the clones of the results that hold in classical category theory. So in particular, what I'm going to say, all the things that are going to be true will hold true for the infinity-categorical setting for this adjunction. So let me list a few results. So first, the first thing I want to talk about is that how do we construct an adjoint functor? So let's say we are given a functor, say f from C to D. It is a functor between infinity categories. So in classically, and actually because the notations are not going to be conflicting with each other, you can think either infinity categorically or classically. So if we have a functor, the question is that how do we construct, or what data do we need if we want to specify the right adjoint of this functor f? So the result is, as you would expect, that is f will have a right adjoint if for each object, say x in D, you can find an object, which I will call it denoted by gx, to imply that it will end up being the image of the right adjoint functor in C. And also you have, as well as, an universal arrow. That is, you want this object gx is a universal element in certain categories. So you want some universal arrow, that is a universal morphism f of gx to x in D, such that you have this equivalence of mapping spaces. So here, that is basically what you are asking for, is that for each object x, you find an object gx, such that if you think about this composite of maps, then you first use the action of f, and then use this universal arrow epsilon x, so that you end up getting this from here to here. And as long as this is going to be an equivalence, then this universal property will allow you to assemble all this data together to get a functor G. So you can find then exist right adjoint G, which, as you expected, stands x to gx, and the co-unit of the adjunction is going to be the specified one. So, and that's the first result I want to talk about. And next, I want to point out that the right adjoint, of course, these statements you can dualize them to get the real statement for its dual. So if right adjoint exists, then it is unique up to equivalence. And this is also something you would like to expect. And basically, you can form a natural, using the universal property to form a natural equivalence between the two candidates if you have two functors that are both going to be right adjoints, and prove that this is going to be an equivalence of functors. And the next thing I want to talk about is that the adjunction passes to functor categories. So all these are just going to be very nice properties, and which are parallel to the results in classical category theory. So this is going to say that if you have an adjunction and you have two functors which are adjoints of each other between infinity categories, and then if K is a simplicial set and E is an infinity category, then you can form the functor categories, and these are the functors induced by this little f and little g are still going to be left and right adjoint to each other. So namely, you can form the functor category So if C is an infinite category, this is going to be an infinite category. So, and you have this induced functors between them. And you can also compose in the other direction. So that is, you have functor from D to E. That is, you pre-compose, and you get functors from C to E. And the results will say that these two are going to still, they are still going to be there are still going to be adjunctions. So this could be checked by exponential rule and triangle identities. So if you have two functors and together with natural transformations in the desired direction, and they're going to satisfy the triangle identities, then they are going to be adjoint functors as you expected. So basically, this is like, for example, here, if you want to check that you have, say, this adjunction between functors, you can think about, well, you extract the data of the unit and co-unit. So for example, here, the unit is going to be a natural transformation between the identity functor and GF. So this could be using the exponential rule. You can think about this as giving you, because these two are both functors on C, so it's giving you a functor from delta 1 to the functor category between C and C. And you can compose this with the functor that is you pre-compose with K. So you get, oops. This functor, you get this functors, and it is easy to check that this composed functor, which is going to be the unit for your desired new adjunction, and they're going to satisfy the triangle identities. So that's how we check that if you have a junction, then the functor category will also inherit these adjunctions in the desired way. All right, so another classical result is the relation between, which I'm going to talk about and end on my topic on adjunctions, is the relation between limits and colimits. So roughly speaking, the classical important result says that first, the colimit functor is going to be the left adjoint of a constant functor, and left adjoint functors are going to preserve colimits. And what I want to claim is that all these results are still going to be true in the infinity-categorical setting. So I will just roughly list them, so to save some time. So if C is an infinity category, which has k-indexed colimits, that is where K is a simplicial category, or simplicial set, sorry. And then you can, for each K diagram, each functor from K to C, you have the colimit of this diagram, and you can assemble all this thing to get, so this gives you a functor, which I'll call colim K, from the functor category from K to C to the category of C. And this is going to be the left adjoint of the constant functor from C to the functor category from K to C. And it's the dual statement holds for limit. And another result, as I mentioned, is that left adjoint will preserve colimits, and right adjoint functors will preserve limits. And one more result, which is also worth pointing out, is that if you combine the results I have talked about, that is the adjunction passed to functor categories, and these two results, you can actually prove that another proposition, that's the constant functor, that is this one. This functor preserves limits and co-limits in the desired, as long as you have the completeness and co-completeness of the categories you have at hand. So preserves limits and co-limits if C is complete or co-complete. So I believe that's the most of the results on adjunctions, which I would like to talk about. So before I move on, let me double check if you have any questions.
Yeah, can I ask a question?
Yes.
Yeah, can you go back to the previous slides where you talk about how right adjoint was constructed? Yeah.
Oh, here.
Yeah. I feel like you only talk about kind of the definition point-wise. Is there, like, say, any higher structured details in this argument? Say, why does this give you a right adjoint functor?
Oh, I see. So I believe first I want to point out this: the proof of this can be found in the lecture notes of Marcus. And secondly, if I remember correctly, I think the adjoint could be constructed by those like the lifting properties appropriately. So I think the data here is enough for you to actually obtain the right adjoint functor.
Okay, and everything is up to natural isomorphism, something
yes,
like that.
That actual equivalence
okay.
in the functor categories.
Okay, great. Thanks.
Okay, thanks. So I think that's for adjunction. And yeah, I try to go over some of the proof sketches, but unfortunately I find it is actually maybe not worth it because it's really not easy to go down to every details. So I already didn't say everything I wanted to say. So in the next part of the my talk, I will try to be more loose and say more about presentable infinity categories and why we are interested in them and some nice results that are going to hold in these settings. Okay, so I think there are several reasons that's why we are interested in presentable infinity categories. So first, presentable. Let me first give you the definition of a presentable infinity category. So an infinity category C is said to be presentable if first C is co-complete, that is, it has small co-limits, and another thing is called C is accessible. So in fact, it will be a very long chain of definitions if I want to go all the way down to end up all these definitions. So I will just roughly say that a presentable category, infinity or infinity category, is something that is co-complete and is reasonably small. So a accessible category is something like this category could be constructed by filter co-limits from like a small set of elements in some suitable way of smallness. So let me keep myself from going into all the details and defining everything, but say that the first, at present, let's just say that this is co-complete and accessible, where accessible means it is small in some sense. So the reason why we care about presentable infinite categories, as far as I can tell, are several reasons. The first is that we have a joint functor theorem, which is actually the main point I want to talk about. And secondly, we can define tensor product between in the infinity category of presentable infinity categories. And this is something which I would put or going to talk about briefly in my next talk. And thirdly, I think presentable categories are nice enough to compare with model categories. So in some sense, and I will going to be able to briefly say something about it. So, well, why not I just go back to Adjoint functor theorem later and first say something about this. So I think the reference for this part is mainly higher topo theory, where Lurie spent like a very long chapter 5 to go one step from your meta embedding to adjunction to accessible categories to presentable categories, all the way to presentable categories, and which is a good reference if you want to learn the details about it. And in this reference, as I believe this result is let's see, is in the A.7.7 3.7.6 in HTT. This result gives you something like, if you have a presentable infinity category, it is in some sense equivalent to the nerve of a suitable, well-defined model category. So that is the setting of presentable category, infinity categories, you are doing this equivalent thing in it as model categories in some sense. So if you are interested in this, you can also go there, and I will also, if I have time, mention something about it slightly later. Okay, so this box is the precise statement of what I mean by presentable infinity category could be compared with model categories. So so now let's jump back to this adjoint functor theorem. So we have already seen that left adjoint functors are supposed to preserve colimit. So that's a necessary condition for a functor to be a left adjoint. So, and people are going to ask, what are the necessary and sufficient conditions? So if F is a functor between presentable infinity categories, then F has a right adjoint if and only if F preserves colimit. So that is in this infinity-categorical setting, presentable infinity-categorical setting, you do have this as an equivalent relation. So a functor is going to has a right adjoint if and only if it preserves small colimits. So you might want to ask, what about the dual statement? That is, what about a function being a right adjoint? And unfortunately, you are not going to have the same result. That is, you cannot say if a functor preserves limit as a functor between presentable infinity categories, then it is going to have a left adjoint. But what you can say is that if F C to D between, you can add just some more mild conditions to guarantee that it has a left adjoint. So if you have a functor between infinity categories, then F has a left adjoint if and only if F is accessible and preserves limits. So here we again make this annoying terminology of being accessible. So this is sort of saying that it preserves some kind of kappa filtered colimit for some kappa. So this has to not only preserve limits, but also preserve some special kind of colimits. So that's the two theorems that are very important, and I cannot get rid of them for this talk. And if you're interested in the proof of them, so I want to point out that in Marcus' notes, it proved a stronger result is proved. And it is not very long. And of course, in higher topo theory, you have the proof, original, or not original, but the more standard or down to earth proof that you don't impose some more conditions or you are proving the result as I wrote. So it's not a stronger result. Also proved. Okay, so let's think if there's something else about this adjoint functor theorem I should say. Well, so yeah, if you are interested in some motivations, I can say that the idea of the proof is to reduce finding such adjoint functors to finding some initial or terminal objects in some slice or co-slice categories. So classically, you have adjoint functor theorem, which I learned about in the book of McLean, the categories for working mathematicians. And there you can find the classical proof. And if you want to have the adjoint functor theorem, that is, if you want to have that the preserving of co-limits is sufficient for having a right adjoint, that is, to construct such a right adjoint, you want this category not being too large. So you want to have some so-called solution set condition. That is like you have a small set of options or generators of the category, so that you can use this small set to define, because the category has small co-limits. So if you have a small set of some nice object, you can form co-limit within them and end up getting the terminal or initial object you are looking for. And this proof will follow this idea, but put things in an infinity-categorical setting. All right, so that's one of the advantages of presentable infinite categories. And of course, the category of spaces is a presentable category. And also in next talk, I will talk about some category of spectral objects, which is also going to be presentable. So these are some examples. And let me go over another part which Lurie emphasized a lot, but not appearing in the notes of Marcus, about the benefit or how do we study presentable infinity categories. So I'll just abbreviate it as a presentable categories. So in the main theorem, I believe is 5.5 in section 5.5 of higher topo theory. Lurie proved a bunch of equivalent conditions for infinite category to be presentable. One of the most important results is that C is presentable. It's equivalent to C is equivalent to a localization of some pre-sheaf category. P of S. Maybe should I say S? P of D for some small infinity category D. So that means that a presentable category can be characterized equivalently as something called localization of a pre-sheaf category. And in fact, I think I missed the term accessible localization. So of course, I would like to say what is a localization. So in this higher algebra setting, a localization, a functor f c to d is a localization. It means that it has, if it has a fully faithful, accessible, sorry, this is an accessible localization. Fully faithful, accessible right adjoint. So that's the definition of a functor being a localization functor. A localization functor is a functor which has a fully faithful right adjoint. So, accessible localization requires the right adjoint to be accessible, which is also something you would expect, because in this the second adjoint functor theorem, you say something is if it is a functor between presentable categories, it is a right adjoint. You require it to be accessible. So that's here also. This result is fine. That is, we expect that this localization has to be accessible. So what is more that we can say is that actually it is also a fact is that accessible localization. This is easy to see that accessible localization of presentable category is presentable. So the study of presentable categories is the same or amounts to study. So we want to study accessible localization of pre-sheaf categories. So this is the functor category from the opposite category to the category of spaces. All right, so and there you can refer also to higher topo theory for very systematic study of localization factors. Basically, what I want to say is that if you have a presentable category, its accessible localization are somehow well understood. That is the localization, accessible localization of the presentable category C is in 1-1 bijection, at least maybe modular some relations, but it's somehow determined by the so-called class of suitable classes of morphisms in C. So this class is supposed to be strong saturated. So this is the terminology, which I'm not going to define, and small generated. So roughly speaking, that is, if you have so the idea is like if you have an infinity category C, and you let say S be a small set of, or maybe not small, a set of morphisms in C, then you can construct so strongly saturated means this collection set of morphisms is closed, say under, push out, retract, and so on. It's a closeness property. And small generated means that this is like generated by a small set of morphisms under this closeness property. So if you have a presentable category C and you have a set of morphisms, you can always find S contained in another set of morphisms. This is so-called strong saturated small generated. And if you have such a class of morphisms, what you can do is that you can form a localization of C. So you can form a localization from C to a new category, which you sort of like you invert the morphisms in this class, and the image of this functor is supposed to be going to be the S local objects in this presentable category C. So that is well, I guess I'm running out of time, so I'm not going to define. I think I had the impression that some speakers talked about this before, but anyways, that is if you have a presentable category or the accessible localization of presentable categories could be characterized as localization at a nicely formed morphism of morphisms, such as, or say equivalences. This is not very interesting, but there are some other interesting examples that you would localize. And all these stories are going to have a nice parallel to the Bausch field localization in model categories. Okay, so I guess before I stop, I want to mention one more thing which I forgot to talk about. So I recall that I mentioned the result that the constant factor, where is it? The I'm confused. I may have messed up with the order of my slide. Anyway, that's fine. So I said that constant functors preserves limits and colimits. So if you have a presentable category, you can have that the constant functor will have a right adjoint because, so let me finish this here. So combine with adjoint functor theorem. So if C is presentable, and because constant functor from C to the functor category, K to C, preserves colimits. So it will have, so it gives the adjoint functor theorem gives you that you can check that the conditions hold. So it gives you that this has this functor has a right adjoint. So this actually gives you that presentable infinite categories are complete. So in the definition, we only require it to be co-complete, but with the the result of adjunction and the adjoint functor theorem, we can prove that presentable infinite category is also complete. Okay, so I guess that's all I want to say for today. Thank you.